Okay, let's talk about the efficiency of the Carnot cycle. So there's a certain amount of energy that would be delivered to a heat engine from maybe a chemical reaction, burning something, burning coal, wood, gasoline, whatever it shall be. That heat enters, okay, through some mechanism, and then there's some pressure volume work done, probably by pistons or something like that, and then the heat that's not used is expelled either through exhaust or just simply out to the environment. So the heat reservoir we call the hot reservoir here, and then the cold one is the exhaust or whatever energy that's not used. We can provide an analogy for this. Let's say there's 15,000 joules delivered by some mechanism, a chemical reaction or something, at 850 Kelvin. And then some of the energy is used as pressure volume work, and let's say that that turns out to be 6,000 joules. The remainder of that is out into the cold reservoir, the environment, whatever you want to call it. Let's say it leaves at 510 Kelvin. Okay, now by difference, we can take 15,000, minus 6,000 and get 9,000 joules. That's the amount of energy that's not useful to the engine, again, as exhaust or just simply being reflected or radiated out to the environment. So we can look at efficiency in two different ways. The efficiency of a Carnot engine is work done divided by the heat flow that entered at the hot reservoir. So then I can just take 6,000, and that'll be joules. I'll divide that by 15,000 joules. And then I just times that by 100. And that turns out to be 40%. So this is a 40% efficient heat engine. Another efficiency is temperature hot minus temperature cold divided by temperature hot. And again, make sure they're in Kelvin. So I'll take 850 minus 510 divided by 850, and then times that by 100. And again, we'll get 40%. So we see that the efficiencies are done in the same fashion. Okay, now what about this? Let's say this right here, the 6,000 joules of work, is really known as the output. Okay, so that's the output work, okay, that we're trying to do. Okay, the input is the 15,000, the output is this. So what if we know the output, okay, of this particular engine, and we know that it's 40%, and we may not know some of the other things here. So I can just use this equation here. Work done divided by Q hot is going to equal the efficiency. So what I can do is I can say 0.40 is equal to the work done, 6,000, okay, then divided by X. And what we end up doing then is taking the 6,000, okay, and divided by the 0.40, and that's where we get our 15,000. So depending on what's given in the question, how the question is asked, you can just kind of manipulate both of these equations and deal with the efficiency of it. Now, efficiency, again, is guaranteed to not be 100% by the second law of thermodynamics. There's always some energy loss that's not used, and there's also entropy that's created that's not really useful to the heat engine. You can't really create pressure volume work out of the increase in entropy that does occur for the universe. And I know we talked about this in class. So entropy is a measurement, okay, of heat flow for a reversible reaction, divided by temperature in Kelvin. Okay, so that will account for some of the fact that all of the heat that comes into the hot reservoir is not useful for doing useful work for the engine.